Hey there, everyone. Welcome back. We've got another exciting week of hopefully some more additional automotive knowledge. This week, we're going to be taking a deeper dive into the actual emission control systems in a vehicle. And so last week we were talking about fuel injection. You're going to see that a lot of these things all tie together, but what we're really looking for is what's that end result that's coming out of the tailpipe. And in many cases, the chemicals that come out have a direct effect on our lives and our quality of life in health. So we're going to define some of those fundamental terms that are related to automotive emission control systems. You'll know in California, we've got pretty strict emission categories. We're going to identify the sources of that air pollution that California was so well known for. And then we're going to look at some of the operating principles of emission control system. What are they actually trying to do? And then we're going to compare a bunch of different designs. Like, how did different manufacturers go about trying to control this? In addition, we're going to look at how the computer or actually the engine control module integrates with this emission control system. We're going to take a look at the operation of the exhaust gas sensors, specifically the oxygen sensors, and looking at this air-fuel ratio or the stoichiometric ratio we've mentioned in the past. And again, all of this is to kind of get you prepared for the ASE certification test, and then even perhaps later on, maybe you're thinking about getting your smog license. All right, so let's jump right into it. Emission control systems, right, are used on automobiles to reduce the amount of harmful chemicals that are released. And there has been a number of strict laws that are aimed at reducing this air pollution, and it's enforced by our federal government, by the EPA, and then, of course, some of our local authorities. And auto manufacturers have implemented these design changes to meet those emission standards. Now, when we burn or have unburned pollutants produced by a vehicle in their fuel systems, we produce chemicals that come out. One of the main ones is hydrocarbons, HC it's known as, and that's the result of unburned fuel into the atmosphere. Simply setting a cup of gasoline out that evaporates would release hydrocarbons. Then we got that carbon monoxide. Those are those toxic emissions that are coming from partially burned fuel, and they're colorless and odorless. In addition, we have oxides of nitrogen, or NOx we call them. Those are produced by high temperatures during combustion. And that is partially, probably one of the main contributors to the smog and ozone production that we've heard about. We also need to look at something called particulates. These are solid particulates of carbon. This is soot or ash, sometimes those plumes from diesels. And this creates problems in our atmosphere with how water bonds to those little particles. Here you can see the air-fuel ratio that we're always trying to get to, that 14.7 to 1. This is our stoichiometric ratio. If we go one way or the other, we're going to push that engine either leaner or richer. And you can see here, as we push lean, we burn hotter and NOx go up. If we push to the left, we get into the richer zone, yes, we're going to have more unburned fuel and higher hydrocarbons. That should make sense. We're running rich. Now, sources of this emissions that happen in the vehicle, crankcase blowby fumes that's coming out of that crankcase. Those are in the engine bottom. There's byproducts that blow past the piston rings and into the crankcase. Additionally, we have fuel vapors, and those fuel vapors have a bunch of different chemicals that just simply evaporate into the atmosphere. And then what actually comes out of the exhaust gases, those are coming out of the back end of the tailpipe. Usually those are our hydrocarbon-based fuels that are being burnt. So a number of emission control modifications have happened to try to help with our emissions. So we've tried to make the combustion chambers smaller so we have less surface to volume ratio. This creates less combustion heat that enters that cylinder head, and more heat is left to actually burn the actual fuels because it's really controlled. We reduce these quench areas and that creates a smaller space between the top of the piston and the cylinder head, which lowers our HC and CO emissions. We have decreased our valve overlap, which reduces exhaust emissions and increases the actual smoothness of the engine. Yeah, when you hear a car running rough, usually that's because of rough usually the overlap, those drag cars that we know about. The higher operating temperatures are desirable in our car. This produces a more complete combustion, and we're running leaner fuel mixtures, which helps move more air right into the system on a leaner condition, and this helps to lower HCNCO. We've also got wider spark plug gaps. We got hotter spark plugs that ignite that hard to burn fuel area in that lean air fuel mixture condition. We have hardened valves and seats that actually are resistant to these higher temperatures. And then we've added these clean burning substances to our actual fuel systems to additionally help us with this reduction in emissions out of the tailpipe. Now, some of the systems that we use, the PCV, this is our positive crankcase ventilation system that helps recirculate the crankcase fumes back into the combustion chamber to be burnt. We have an EVAP system on the car. That system is designed to capture those evaporating emissions of the fuel vapors that are coming off of the car, reintroduce them in so that we can burn them. We use exhaust gas recirculation. This system is designed to enter gas that's been burned and reduce the temperature in the combustion chamber. We have air injection, which forces outside air into the exhaust system to help light off that catalyst during our cold starts. We have a catalytic converter, which is designed to chemically change the combustion byproducts into harmless products for us. We also have a computer control system, which allows the vehicle to take in sensor readings and adapt more quickly to any types of changes in the operating conditions that are occurring. All right, let's take a closer look at some of these systems. These blow-by gases, or the engine blow-by, is caused by pressure leakage. It gets past the piston rings during the power stroke. That engine blow-by contains unburned fuel. It has partially burned fuel. There's particulates. There's small amounts of water, sulfur, and acid that actually are harmful to the atmosphere if they get out there. And so what we're going to try to do is capture that and re-enter it. That air pollution that happens during this is released into the atmosphere if it's not treated, and this also leads to the corrosion of engine parts from the acid buildup that's in the used oil. We still get it in there, and that's why we have to do oil changes. The engine oil dilution happens from the fuel contamination that's actually in that mixture that blows by those piston rings, and then we end up with a sludge formation once that oil starts to break down. Now, the positive crankcase system, a closed PCV system, has a sealed oil filler cap. It has a sealed oil dipstick. It also has a ventilation number of hoses related to it, and either a PCV valve or a flow restrictor, sometimes called a swirl restrictor. The crankcase gases are drawn into the engine and burned this way so we can capture them, reintroduce them, and we store the gases when the engine is not running down in that bottom end. The hose usually connects to the intake manifold to the PCV. With the engine running, the vacuum acts on the crankcase gases, and air is drawn in through the engine's air cleaner through this vent hose into the valve cover and down into the crankcase. We're going to pull those fumes in and burn those and actually use them as an energy source, which is a good thing. We're helping getting them out of the crankcase. Additionally, with this system, after the fresh air mixes with the crankcase gases, the mixture is pulled by that vacuum right up into that intake, past the PCV valve or the swirl unit, through the hose and into the engine intake manifold. This crankcase gases are then drawn into the combustion chamber with the fuel, and then this mixture can be lit off and reburned. So we're really recycling these fumes back into that combustion chamber. This PCV controls flow of the air through the PCV system, that valve. It's located in usually a rubber grommet in the valve cover. It's in the breather opening in the intake manifold or plenum, depending on the vehicle, or sometimes in the side of the engine block. Now, the PCV valve varies flow of air for idle, cruise, acceleration, wide open throttle, and engine off condition. So it has a little spring in there. Usually if you shake these around, you can hear it rattling inside. These are all tempered for that situation. Now, some of the newer cars are using what they call electric PCV valves, and they use actually the ECM to control control to regulate that engine crankcase ventilation. And those electric PCV valves, they have a small solenoid in there that allows them to regulate the air. And you can imagine that these can be controlled very precisely by certain sensors in the vehicle, with the ECM knowing when it needs to actually open or close that system. Now, the EVAP system, or Evaporative Emissions Control System, here is for the non-vented fuel tank caps. This prevents fuel vapors from entering the atmosphere right through the tank's filler neck. This is really important. This is why you actually see when you fill up a car, it's got a little stopper there. This is a charcoal canister, and that stores fuel vapors. This charcoal wants to bond with it when the engine is not running. So as that stuff's evaporating, it's sticking. And then that container is activated with this fuel that happens through a purge line that removes the stored vapors from the charcoal canister. So this purge valve opens up. It allows air to be drawn in from outside over the charcoal and then towards the intake manifold. And then this hump that's formed in the top of the fuel tank allows for fuel expansion and the tank filling without spillage, so that this thing expands back and forth. Otherwise, we might have some problems. Now, there are metal gas tanks out there. Most of them today, though, are plastic. We also have what they call a liquid vapor separator. This is a small valve sometimes used to keep liquid fuel from entering the evaporative emission system. There's also what they call a rollover valve, and that's used in the vent line from the fuel tank. Both of these systems are designed to keep fuel from entering, actual liquid fuel entering the vent line, especially if the vehicle rolls over or is being driven in a dramatic fashion. All right, so in this visual here, you can see on the left-hand side, we got the fuel tank. The bottom half of this has the liquid fuel. The orange top portion is that vapor. You can see the rollover valve there if it's activated, if the car was to be upside down. But normally, this allows just vapor to get past it over to that charcoal canister, which is then routed to the intake manifold. There's a purge valve that's involved. When the system commands the purge to open, it draws fresh air in, sucks that air over the charcoal, and brings in the fuel mixture. Now, on the EVAP system, we need to be aware of some sensors. We have a fuel tank pressure sensor that monitors the internal fuel tank pressure, and that sends a signal to the control unit. This is a very important sensor. That's how it determines if purging is happening. Then we have a canister vent solenoid that's electronically operated, what's sometimes referred to as the back door, and that replaces fresh air. Replaces the fresh air vent used on older canisters. Then, of course, there is a service port that allows us as technicians to connect to this system to determine, what's going on in the system when it's been activated. This fresh air is then fed to the canister by the vent solenoid. That purge valve or purge solenoid, which would, if it was a solenoid, would be electronically activated by the powertrain control module. And that valve controls vapor from the canister to the engine intake manifold. So in other words, when the purging is going on, it's drawing this vapor that's been collected into the intake manifold to be burned. Now, the exhaust gas recirculation, or EGR system, allows burned exhaust gases to enter the intake manifold. Why would we want to put exhaust in the intake manifold? Well, we want to slow down the combustion process. That drops the heat and reduces the NOx emissions. So this is what we're trying to do, is control that peak pressure or peak temperature. The EGR system can be controlled by engine vacuum, or it can be electronic. Most of the late models, though, may or may not use an EGR system. They can do it through the cam adjuster. Now, the electronic EGR system, the vehicle sensors that are involved, the ECM and the solenoid, operates the exhaust gas recirculation valve. The sensor signals allow the ECM to determine how much duty cycle or how much of this exhaust should be reintroduced. The EGR is usually duty cycled, and that measurement of the control current on and off time is sent from the ECM itself. Now, the powertrain control module and the EGR system are integral. They're looking at the oxygen sensor on the vehicle. They're looking at what's coming out of the catalyst and what is the position, right? The position sensor. And then based on this information, it can calculate how much EGR we can use. Typically, EGR is introduced when we're coming off of the throttle, decelerating. Here, the electronic EGR valve, one or more electric solenoids can be opened and closed at certain exhaust passages. And this system works without engine vacuum since it's electronically controlled. There's multi-stage EGR valves, and those can use more than one solenoid valve, which really precisely controls the amount of EGR gas flow to the engine. Too much EGR gas recirculation, the engines are usually stumbling. Now, electronic vacuum EGR valves use both vacuum engine vacuum and electronic control. The EGR position sensor usually sits on top of this valve and sends information to the engine control module. The engine control module determines how much EGR valve needs to be open to control that flow. And the EGR solenoid valves have EGR. The EGR, this regulation occurs based on that input. The electronic vacuum EGR, you can see here, has two different inputs going into it to determine the engine coolant temperature, what that air volume is, throttle position, of course, crank angle. All these inputs are derived to determine how much vacuum and how much electric signal need to be added to get this very precise movement of that valve to reintroduce EGR back into the engine system. All right, the next item up here is the catalytic converter. This is enclosed inside this high temperature afterburner that's in there that's chemically treats pollutants. So there's some precious metals that are inside this unit, and they're designed to react with the chemicals that are passing by it. That helps us basically scrub the air, more or less. We're going to clean up the air that we're actually going to let out the tailpipes. Now, when we do this, there are different types of catalytic converters that are out there. There's a mini catalytic converter. This is a small converter placed close to the exhaust manifold, and this is actually a fairly popular design even today to get it hot. There's also what they call a two-way catalytic converter, or basically this is known as an oxidation catalyst. And these reduce two types of emissions initially. These were HC and CO, and this was our initial attempt on many vehicles to start doing this cleaning. Today's vehicles, most of them are using what they call a three-way catalytic converter or reduction type converter. These reduces HC, CO, and NOx. You'll see that there's a dual bed, or there's two different sections in this that are used inside this housing to create this three-way catalyst cleaning that happens. Now, it's very important that the engines are running between this fuel control system, this rich and lean condition. Couple of tips to know about catalysts in particular is that some are coated with materials that absorb and temporarily store NOx emissions. And then when the saturation level is reached, the onboard computer temporarily will enrich the fuel, which allows the converter's internal honeycomb structure to block and glows red hot, breaking up the stored NOx emissions into harmless byproducts. This goes on quite a bit. We'll learn more about that with diesels as well. There's a system. So the emission control management system itself, right, is used on various engine styles, exhaust, and fuel systems, so they're all a little different. However, most of them do have a three-way catalytic converter on them. Most vehicles that are out there are going to be using dual bank O2 sensors measuring pre and post catalytic converter operation. The ECM is analyzing the data from all these systems that affect the air pollution to determine if there's any issues. It is critical that these systems have oxygen sensors for the engine performance and for gas mileage. The ECM uses at least two of these sensors to control the main fuel control, and it tries to keep this engine running in that stoichiometric range, that 14.7 to 1 ratio. Now, the number of O2s depends on the engine, the application, and whether the engine has single or dual exhaust pipes. We may need more or less. So let's talk a little bit more about these oxygen sensors. The primary oxygen sensor, what's normally called the front O2 sensor, monitors oxygen in the exhaust gas that's actually coming out of the engine. Now, When the secondary oxygen sensor, the rear O2, what's called a post O2 sensor, is mounted downstream of the exhaust, primarily after the catalyst, and it checks oxygen content of the exhaust gases entering the catalytic converter or monitors converter operation. It's really controlling long-term fuel trim. Now, the oxygen sensor position is located typically pre and post CAT. So you'll see that one might have a heated O2 sensor way in the front, close to the manifold. This is before the catalyst. And then we may see one if it's got dual banks on each manifold, exhaust manifold, and then one after the catalyst. This is also that the system can actually check that the engine is indeed running as designed in fuel control. Now, there's different types of oxygen sensors that are out there. There's heated oxygen sensors that have an electronic element that's used to heat up the sensor quickly. There is what they call zirconia oxygen sensors. They use zirconia and platinum to produce a voltage that represents the oxygen. These sensors react to oxygen content in the air, but they have to be hot to do so. The ECM compares voltage produced by the sensor to what they know as a reference voltage. There's also a planar zirconia oxygen sensor, which works very much in the way of the conventional zirconia sensors. This has a zirconia element, an electrodes, and a heater combined into a flat laminate strip internally. There's also what they call a titania oxygen sensor, and that varies internal resistance to modify the reference voltage. These are not as common and are only used by one manufacturer. The most current O2 sensors that are being used are called wideband oxygen sensor or fuel ratio sensors. These generate a variable voltage or what current output that signal proportional to the engine's present air-fuel ratio. The ECM uses this data to control the fuel and the ignition system. These sensors have a little pump in them that actually is trying to keep the air equal on the outside of the sensor. Now, the emission system monitoring that goes on, there are the list of the systems that are monitored. The catalyst, the engine misfire, the O2 sensors, EGR, fuel injection, air injection, and EVAP. And not every vehicle has all of these systems, but most scan tools will be hooked up to check those systems. If you ever hear the term, I'll have the monitors run, this is what they're talking about. Each one of these represents a monitor. If one of these monitors detects a problem, the engine control module sets a trouble code and then turns on a malfunction indicator light. Most of you are aware of this because you're probably familiar with the check engine light. The check engine light directly is an indicator of an emission failure of some sort. If the problem can damage the catalyst, the ECM flashes the mill once per second. These are considered like cat damaging codes. Now, the evaporative emission system also has a monitor, and that's checking the components for leakage and restrictions that could potentially increase emissions. The ECM energizes the solenoid valves to seal the system. This is that back door I was talking about. It allows the computer to detect leaks or blockages by using that fuel tank sensor, pressure sensor. The ECM, if it detects a trouble code, does not pressurize and depressurize normally. Now, EGR monitors itself as well, and that's done with the ECM, and that turns the EGR off while checking to see if the O2 sensors react. Changes in EGR valve opening and closing affect the air-fuel mixture, and therefore the O2 sensor readings will change. Changes in EGR valve that do not affect the O2 sensor trigger a trouble code and indicate to the technician that there's something wrong in the EGR system. All right, so now there's another monitor called the catalyst monitor, and sometimes this can be a little bit confusing because it's also called the rear oxygen sensor or secondary oxygen sensor, and it's always located after the CAT, as I mentioned previously. This checks the oxygen content of the exhaust gases after exiting the catalytic converter to determine if the catalyst elements are actually doing their job. If you see a low efficiency CAT code, this usually is an indicator by that sensor. If the catalyst converter is not cleaning the exhaust gases as it should, the catalyst monitor signal becomes too similar to the engine-mounted oxygen sensor. So let me just point this out. On the right side, the top one, you can see the waveforms going up and down. We do not want to see that. If you look all the way at the bottom, that's the rear O2 sensor. If those two sensors look similar, the engine turns on the mill light. It knows there's a problem with the catalyst itself. Now, the engine misfiring monitor is using the engine crankshaft position sensor to detect changes in crankshaft speed. And this may indicate the engine is missing or not firing air-fuel mixture properly. Misfire is what we call this. If the crankshaft speed fluctuations are detected, again, the ECM is going to trip a trouble code. This is usually a big one because if it's misfiring, we could be getting the catalyst too hot. It's cat damaging code, so it's usually a priority 1. So sensor monitoring of this system uses ECM data, and it's sitting there and it's comparing these known normal sensor signal variations to what the actual sensor signals are, sometimes called mapping. If the sensor signal goes out of range or out of a parameter, again, a trouble code is set. So these are pre-programmed from the factory into the computers. There's what we want to see. This is how it should be within this operating range, and it's looking to see if that sensor goes outside of that. Now, the actuator monitoring, the ECM uses the digital data, determines if an actuator draws too little or too much current. Think of it like a little amp meter itself. It's measuring the amperage. The ECM system detects problems in actuators and actuator circuits for the fuel injectors, the electronic variations of the EGR, the evaporative solenoids. High pressure mechanical fuel pumps can even be detected on some of those control side systems that are electrically controlled. All right, lastly, I want to talk about the diesel particulate filter. There's a lot to diesels now. Diesel particulate filters are what they call a particulate converter, and they store what's known as and burn ash or soot that is left by diesel fuels because it's not quite as refined. The ECM has to alter the diesel engine operating parameters to actually cause what they call a blow of flame out of the exhaust ports to superheat this burn-off period. This crude oil that soaked soot inside these particulates filters is then burned up under that high temperature, and this is what greatly reduces the emissions or the exhaust sooting. This was a major requirement for the commercial industry with these vehicles. All right, so once again, guys, that's a lot of information, and I don't expect you to be experts on it. A lot of our training keeps going more and more into depth on each one of those topics. So again, nice overview, good general idea how these different systems are working. You're being exposed to it. If you have any questions, I always encourage you to reach out to me. I want to try to help you out as much as I can to understand these systems, and then just know that down on the road you'll see these systems. Thanks again, guys. Bye.